Yeah, so this is in theme with the conference. I have field theory and turbulence in the topic. Okay. This is field theory for turbulence is old field. There are a lot of work. So I have some innovation in this, but a lot of it is, in fact, past work. Okay. So my affiliation I forgot to write. I am from IIT Kanpur in North. So these are some references. I'll have two more references at the end. So D-dimensional turbulence in 1978, Fournier and Frisch. So our D will go from 2, it's incompressible flow. So I need minimum 2 dimensions, 2 up to 6. I find that at 6 there's a problem, which I'm going to highlight. So that may be connected with the critical dimension, upper critical dimension of 5-4 theory. So this is a paper in the archive, and for students, I did try to put this is a 2-hour long video with the details. So if you like to see, if you type this in a YouTube, you'll find this. Okay. So detailed calculation. So these calculations are, if somebody has done field theory, you'll find that these are pretty complicated calculations. So you may find almost all the steps which I'm going to do today. Well, I'll not do the steps today, but you'll find all the steps in this calculation. So why field theory for turbulence? It turns out it's a nonlinear, one of the hard problems of nonlinear physics. So, but few things are very well known. In fact, it was discussed in the first lecture by Srini that K41, Kolmogorov-41 theory is an exact theory. Okay, assuming hydrodynamics. Okay, so Srini said it's not quite convincing, but starting from Navier-Stokes equation and assuming the properties, assuming homogeneous and isotropic fluid velocities, this is derived by Kolmogorov. Under the limit, nu going to 0. Okay, so this is exact, but this is cubic order, and it is proportional to R. But it doesn't say anything about second order, third order, fourth order, fifth order. So it doesn't talk about higher order correlation. It turns out in field theory there has been attempts to compute those orders, including by Gregory Folkovich, who is here, and there are other people who have done lots of work on this. So, so this is what I did: second order, higher order correlations from first principle. The idea is to get this correlation from the first principle, starting from Navier-Stokes equation, derive them. Putting ideas from quantum field theory. So I think this was a major inspiration. So can we apply them here? And it turns out you'll find that they are, in fact, the tools are pretty much similar, except the fields are not quantized here. It's a classical field theory, but tools are very much similar. So I have Feynman diagrams sitting there. So I will refer to them when I get there. So uniqueness of quantum field for hydrodynamic field theory, I would like to emphasize this main central issues. One thing is large interaction parameters. So the u dot grad u, which is the nonlinear term, which is very large compared to viscous term, nu grad square u. Okay, so the ratio is called Reynolds number, and so this is a problem with large coupling constant. If you talk in terms of quantum field theory, still we apply it. Okay, so this is something which seems to give a reasonable answer. I wouldn't say it gives a precise answer like QED, but it gives a reasonable answer from field theory. So it's reminiscent of QCD, where the coupling constant is large, but so that's what I've talked to some high energy people, and they're not so interested. Actually, it turns out I didn't find a real person who is interested to see the connections. So in turbulence, we employ forcing. So so normally we force the fluid. We also apply self-consistent ideas. So we want to solve this problem, large interaction problem, to overcome this large interaction parameter issue. It will be perturbative. I will describe only perturbative. There was some talk today morning about non-perturbative, but this is perturbative calculation, first order in my presentation. So crosstalk, I think, between these two will be useful. I have not been able to get some idea to bridge this gap. Second is non-equilibrium nature. I think this is a very critical part. A lot of statistical field theory calculations are equilibrium. in a heat bath. Even I believe QED is a equilibrium calculation. It's not a non-equilibrium calculation. So here in hydrodynamics, but this energy flow from large response scale is a key ingredient, and that differs from equilibrium system. So frequency is a very key component for our field theory. So detailed balance is broken. There's no heat bath. In fact, there's no temperature for Navier-Stokes. For other systems like convection or compressible turbulence, there's temperature. But here I will have no temperature in this. So correlation function is not same as Green's function. This is one of the things which we have in most of the 5-4 theory. We have Green's function, which is same as correlation function. But it is not the case here. We need to compute them separately, and I'm going to show you how to do it. Okay, and with forcing, so there are several ways to do these calculations. So I'm just giving names. I can't really go into details. So Yochod-Herzog, that was a paper in 1986. This is a pioneering paper. But before that, there's a Foster-Nelson-Stephan, which Rahul mentioned in one of the slides. So this is these are the pioneering work. So with forcing, compute these quantities. Martin C.J. Rose, MSR, nonlinear PDE, so I'm going to follow McComb and Zhou. So these are self-consistent theory. I will follow this scheme for today's talk. But I will do mention about how to go about, what happens here briefly. So one more point which I completely agree with Srini, that the turbulence world is very, very varied. There are different types of turbulent phenomena. For example, magnetohydrodynamics, where magnetic field plays a big role, is mostly anisotropic, inhomogeneous, pipe flow, convection. They're all inhomogeneous, isotropic, multi-component flows. So here, field theory can help, and people have attempted to use field theory, but there are complications. I think they're not easy to apply. For example, there is no very good field theory for turbulent convection. There are some work, but not many. Rotating turbulence, plasma turbulence. So here, Yochod-Herzog is a it becomes too complicated for attempting these problems. And some of it remains unsolved. We really don't have good work in this to solve the problem. Unfortunately, there are very few people who work on turbulence, application of field theory on turbulence right now. There are more people in the past, but it has basically, this field is, I guess there's no funding, or it's not very hard, or maybe not important. Machine learning is more important. So that's how people have left this area. So we need to devise clever schemes. So, okay, so these are problems we should be able to get some idea from field theory, but not much is happening right now. So I'm going to apply Eulerian framework. Though there are some issues which is pointed out, like sweeping effect is not well taken care of in Euler framework, but still I stick to it. It gives reasonable answers. So this, I'm not going to follow Lagrangian, which is much more difficult. Okay, I share this sentiment that there's no universal theory of turbulence because of these. There's one theory cannot explain all of it. Okay, so practical applications. It turns out what we learn from field theory straight away gets into large eddy simulations. So this parameter, so for Earth simulation, for climate simulations, the grid is something like 2 kilometers by 2 kilometers. There I cannot put the viscosity of water as 10 power minus 2 centimeters square per second. That won't work. So we need to model this viscosity at that scale, which already has turbulence in it. So that's why for bigger grids, we need to model viscosity. So large eddy simulation is a very good place where these ideas go in, and viscosity is at unresolved grid. Now I do want to make this remark. So the diffusion in this room, for example, in the school textbooks we see that the diffusion of dust particle in this room is following Brownian motion. Totally incorrect. That's not a Brownian motion. It's a Taylor diffusion, and the Taylor diffusion is purely by hydrodynamic effects, and that is what is this viscosity at unresolved scale, or diffusion parameter at unresolved scale. So it is a diffusion which is, in fact, just to give a slight hint, that the diffusion length goes as t to the power 3/2, not square root t. So this is not Brownian at all, and this is hydrodynamics. Okay, this is connected with viscosity at large scales. So it's hydrodynamics. So let's now get to the field theory. So I've given the background for 10 minutes. So now I'm going to go to the real calculation. So I'll try to go slowly, but give you the gist, and hopefully you see how it is done. So the idea is that we start with Navier-Stokes equation, and I will try to see how viscosity goes from increases when you go to bigger and bigger scales. As I said, the diffusion of a dust particle in this room is not by Brownian motion, not because of diffusion at small scale. So it is because there is a velocity field, which is hydrodynamic velocity field, not the scattering of molecules, that is active at that scale. But if I go to bigger scale, then there is a bigger vortex is playing a role, and that is enhancing the diffusion. So loosely speaking, the viscosity here, in fact, this dimension analysis, viscosity is length scale L, is for in turbulence is proportional to velocity and length. So velocity at length scale L multiplied by L, and this is function of length. In fact, we know from Kolmogorov theory it is epsilon 1/3 L 1/3 is L. So this is the diffusion coefficient at length scale L goes as L to the power 4/3. It increases with length, and that is what is causing the diffusion of dust particle in the room. And this is what is important for diffusion in chemical reactions or all over. I mean, astrophysics diffusion is via this, not because of Brownian motion. And this is purely hydrodynamic feature. So it is basically, well, one point, so this is a kind of pedagogy also involved. So that delta R goes as t to the 3/2. That is at Taylor diffusion. Now, it's very, very surprising formula. How can a diffusion be faster than a ballistic diffusion? Ballistic diffusion, the diffusion, well, if the particle is moving straight with constant velocity, it should be proportional to t, but it's faster than t. Because when we go to higher, when time passes, we jump on a bigger and bigger vortex, right? So bigger vortex has bigger velocity because this velocity is proportional to L 1/3, and that's how we get this. So a joke is that if you want to make a big progress, then you have to hop onto a famous group, that famous group to bigger famous group. So that hopping will take you very far, and that's what happens for these particles in turbulence. So the idea is that it is function of velocity, which is length dependent. Okay, now let's get to that thing. So the idea for RG, so I will follow the renormalization group in Fourier space. So we divide our Fourier space into various shells, K0, K1, la, 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 and I'm going up to Kn plus 1, but there is up to K infinity. But please, so I'm going to say that I already have taken the effects of renormalization up to here. K infinity to Kn plus 1, I already have renormalized. So I'm going to write a recurrence relation. So I'm going to assume that my viscosity, renormalized viscosity at Kn plus 1 is nu n plus 1. And then I will write down what is the viscosity at Kn. And from the recurrence relation, I will derive the formula, which is that. Okay, that's the main idea. So, so this is what I want to derive. Okay. So, so let me write down the equation. So the equation is okay. Before that, this slide is also important. So we have in Navier-Stokes equation we have three parameters: coupling constant lambda, which is the coefficient in front of Euler radio. That's called coupling constant. There is a viscosity nu, and there is a forcing amplitude. So typically we force large scale like Kolmogorov theory, or it may also force small scales. In fact, Yakovlev forces at all scales. So that is the forcing amplitude. We use Eulerian, I said that, but it turns out the lambda, this coupling constant, is not renormalized. It remains unchanged, and that is because of Galilean invariance. In particle physics, this lambda is renormalized, the charge renormalization. This is connected with charge renormalization, and this connected with nu is connected with mass renormalization. So it turns out in Navier-Stokes, nu doesn't change, lambda doesn't change, and the forcing is changes in Yocker-Orzhov, but not in my scheme. I'm going to dump all the RG effects into viscosity renormalization. Okay, so I will not force at all scales. I will force only large scale like Kolmogorov, and I will put everything here in nu. Okay, so I should have written the Navier-Stokes equation. I did not write it, which is a good idea. I think I have it in my next slide. So, so we have three components of velocity field in Navier-Stokes. It turns out we can do that work, but if you work with three components and we have also divergence-free condition, del dot is 0, that involves a lot of algebra. It turns out it's just by accident. If I use Crea-Haring basis, then my calculations are simpler. At least I find it much more compact. I don't need to deal with tensors at all. Tensors are gone. And I think some of it can be applicable to other fields in particle physics. For example, QED, there's a divergence is 0. So I think some of it may be applicable there as well. But anyway, what are these Crea-Haring vectors? So we have wave vector k, and we have anisotropy direction n cap. N cap for hydro, well, my flow is isotropic, but I can choose n cap in any direction. Okay, I choose n cap in any direction. Then k cross n, so k cross n, which is this yellow region, yellow plane. So k cross, this E1 is k cross n, which is perpendicular to this plane. So E1 is pointing towards you. Then E3 is the direction of k. So E3 is along k. So there's no component along E3 because k dot uk is 0. Now my E2 is perpendicular to E3 and E1. So E3 cross E1 is E2. So my velocity field basically lies in this plane, E1, E2 plane. Okay, this is a plane formed by E1 which is coming towards you, and E2 is perpendicular. So my velocity field is that plane. So I have only two components which are independent, and I can write down equations for them. Okay, so this is my velocity field. This one. Now I want to do in d dimensions. So how do I generalize to d dimensions? So this is a sketch again for students. So here I have 5 dimensions. Okay, together. So I have k1 and k2. So my vector k is here. So a project along k1 is k1 cos phi 1. This one, this part, this part. Now I project on the plane formed by k2 and k perp. This is not the component. So k perp. So k perp is again now projected onto this 3D space. So we have K1, K2, K3, K4, K5. So that's where keep projecting on more and more directions, and we find that. Yeah. So this is my 5-dimensional space. I can do it for any dimensions I like. And one important point is that I assume isotropy so that energy of each component is equal. U1 squared, U2 squared, U1 mod square, U1. So they're all equal, and this is I denote by Cu. Now this Ek, which was mentioned in the first talk, it is a k minus phi third. This is k minus phi third. It's called cell spectrum. Okay, so it's a bit detailed. It's so I need to convert this modal energy into Ek. So that's the formula for it. So Ck is the modal energy. For every k, I have energy, which is called Ck, and energy of a shell. So is called Ek, and this is a conversion. Now let's write down the. Okay, before that, so we have two kinds of solution, which was mentioned in today's Rahul's talk. The one is non-equilibrium solution, which is phi third, k minus phi third, right, which was illustrated by Srini. But there's another solution which was told by Rahul, which is equilibrium solution. Okay, it came in Brass's talk as well. So this is where every mode has equal energy. So in fact, we want to see whether this solution is valid or this solution is valid through RG. I'm going to sketch today. I'm going to show you for d equal to 6, this solution is probably coming at large dimension. And for d less than 6, this is a stable solution. I've not done the full proof, but this is what it appears from the calculation at present. Okay, so we'll focus on a single triad. So we have k prime plus p plus q is 0. So these are interacting triad. This is coming from the nonlinear interaction. So u dot grad u term. So in Fourier space, that will be convolution. So our equation is UK dot in the right hand side is UQ. This is coming from the convolution. Okay, so these are the interacting terms, and they form a triad, which is here. So this is a triangle, in fact. Okay, and the internal angles are alpha in front of K prime, beta in front of P, and gamma in front of Q. So this is my triad. Now my unit vectors. Remember, I had E1 and E2. So I have E1 along. E1 is perpendicular. Well, E1 and E2 are perpendicular to the wave number. So for vector K, wave vector K, E1 is perpendicular in that direction, the red arrow, and E2 will be into the plane, which is minus n cap. So these are the gray herring. It's a bit of algebra, but it turns out for 2D, we just worry about all these three vectors: E1 K prime, EP, E1 P, and E1 Q, and E2 is into the plane, very nicely sitting there. So our equation. So this is now RG step. So we have equation for velocity field U1. Okay, now this slide is slightly there are a lot of stuff in this slide. So what I do is I take this full space up to Kn plus 1. Remember, I have taken care of renormalization from here to infinity. So I have Kn plus 1. Now the convolution, which is written somewhere here. So we have, you see, U1 of P and U1 Q here. This is, then we have four terms. So this one will have, so well, we divide our Fourier modes into less, and greater, two categories. The ones which are less than equal to Kn, which is less, greater than Kn is greater. Got it? These are two types of. So if you think of in real space, this is like 5 centimeter, and this could be 50 centimeter. Low wave number means bigger scale. Okay, so we are looking at velocity field for large scales here, and this is velocity field for not so large scale. Okay, so now when I do the convolution, I'll have various combinations, no products: greater, less greater, less, and greater. So this is Wilson scheme. Okay, Wilson scheme. So this is my less part. Greater, less. Believe me, it becomes 0. When I do the integral, it is 0. The one which is not 0 is greater. Okay. Now this is the one in the red, within the red ellipse. Now this is the equation for viscosity nu n plus 1. This somewhat may not look too bright at the back. Nu n plus 1. This is viscosity for all the scales up to Kn plus 1. Now I want the viscosity up to Kn. So when I do simulations at the coarser grid, then I get viscosity up to Kn. So this is nu n k squared. So if I write down equation for all the modes up to Kn, this is my equation. So what's the connection of this equation with that equation? Okay. So here, my bottom equation do not have these three terms. This term, but I told you these two go away. This is the only term which is of importance, this term. So bottom equation does not have this red one, which is missing. So, but my viscosity has changed. So I wrote nu n plus 1 with nu n, right? That has changed. So the idea is that nu n k squared is same as nu n plus 1 k squared, this one, plus this red ellipse that is gone in there. So my viscosity has changed because of the convolution term which I ignored. Okay, so when I look at larger scale, I ignored some interactions, and that is enhancing the viscosity, and that is what is enhanced. So rest all is bit of calculation. Now u greater, we can write down in terms of assuming them to be fluctuations. So 0th order, u is a fluctuating field, so it should be 0, product of two random fields. But to higher order, when I expand it using Green's function, and so I've done it there. So this one of the velocity field, this velocity field here, this velocity field, I'm going to write down the Green's function and to use. So basically write down equation for UK after this, and that will have Green's function and another to use. So this is a standard thing in field theory. So we have So we have one leg here and this guy Green's function and two more legs. But it turns out two legs here, if you just see, two legs can be combined to make a correlation function. What is the correlation function? Is u of q and u of minus q, right? That's is a power spectrum. So that is the power spectrum. So this C1 of q, this C1 of q. So this is the called bubble diagram in field theory, the bubble diagram. Okay, so we have two bubble diagrams, I1 and I2, and if I can compute them, then I know how much viscosity has increased. That's the idea. Okay, now it turns out it has variables C1 q sitting there, and this viscosity nu n is also there. Now I don't know what they are. So in perturbative field theory, normally we put is our bare Green's function, which is like nu k squared, and this is put as some noise. C1 comes from the noise, but in Macomb procedure, we assume that this C1 is my dressed correlation function. That means real correlation function, which I expect. So this is a shortcut. This is a shortcut. I assume that my C1q is following Kolmogorov spectrum. The C1k is proportional to Ek and is 5/3. So my correlation function is proportional to 5/3. That's assumption. And I will put it there and see whether it gives me a consistent solution or not. A viscosity nu1 is minus 4/3. It's coming from here. This scaling argument. I'm going to put these guys here and see whether I get a reasonable solution or I get some contradiction. That's the whole idea. Okay. Now, if I look at the next slide, so this is my equation for nu1 k squared, and I'm going to plug that in there, and this is the algebraic equation. It just needs to be integrated. I can do it in Python, and I can compute this nu1. So my idea here is I want to compute nu1 star. This is a non-dimensional constant, and that's what I want. It turns out the k Kolmogorov gets cancelled. In this integral, you don't see k Kolmogorov, it gets cancelled because of the choice of square root of k naught. Okay, so this is what happens here, and I get nu1 coming out of this theory. I can compute it for any dimensions. It turns out I did this in Python. It turns out till 5.5 I'm okay, it's around 0.1. This number is around 0.1. But at 6, this number nu1 squared becomes negative. If I follow this, it's telling us something, at least it's telling me something, that nu1 star is 0 probably. For d equal to 6, the solution, this part basically is not contributing, hopefully, and is giving us, basically, this is random, like Euler gas, thermodynamic gas. So by the way, the other solution which corresponds to viscosity is 0, where field is random. So this is 0, random field multiplied by random field. If you integrate, it will get 0. I hope I am convincing you that for there is a solution which is like Wilson Gaussian fixed point that corresponds to random velocity field, and that will give us 0 correction to viscosity. Okay. So that is the other solution which is coming at d equal to 6. That is my conjecture at this point. Now we can also compute. So one more point. This is very complicated calculation, but so this is for velocity field component u1, but we have another component u2. It turns out u2 has a different equation and its viscosity is different. It's a bit surprising, but it appears from this calculation that we have two viscosities. In RG, of course, we have more parameters coming out of the solution, but we have two viscosities coming out of this calculation. For one component, other for other component, and this component is around 0.6. Okay, so this is RG calculation part 1. So this is what we get for viscosity. So my viscosity, I have prefactor, I computed them from this calculation. Now what about Kolmogorov constant? So can that be calculated? That was the question asked by today morning in Spenta. It turns out we can compute Kolmogorov constant in this scheme. It's approximate, of course, but we can get it. So how do I do it? So this is what I told already. So let's look at energy flux. So energy transfer from large scale to small scale, how can we prove it? 5 minutes, no, for me. So we look at energy transfer into wave number k prime from other wave numbers. Okay, so we have energy equation, and the energy equation gives us how much energy is flowing from some wave number to some other wave numbers. And the equation is here. So energy coming off from mode P. Okay, so these are 3 wave numbers. Okay, triad. So energy, this wave number P gives energy to k prime by this formula. Well, it looks slightly complicated, but it's not much. There are 3 U's: U1, U1P, U1 K prime, U1P, U1Q, and there's a prefactor. This is called vortex. Okay, this is a prefactor. Now it's kind of nice in this gray herring basis. It's a bit of work, but it looks nice. So I have energy exchange across among U1 channel, in this U1 channel, and also in U2 channel. Okay, so there are 2 channels. So U1 component of gray herring, there is energy transfer, and U2 component of gray herring, there is the energy channel. There is nothing across U1 and U2 because they are perpendicular. Okay, when I compute, well, now I need to compute this. I will assume that U's are random fields, quasi-Gaussian, right? Exactly like 5-4 theory, or even in quantum field theory, assume these fields to be Gaussian, or Wick's theorem you can apply. Okay, so that stuff. Now it turns out to 0th order it will be 0 because they are odd number of random fields. Assume velocity to be 0 mean. So I need to go to the next order. So what do? I take one of the U's and I again do Green's function and 2 velocities. So we write down the solution for U and do it. So these are the free Feynman diagrams. For each U I am going to expand using Green's function and 2 correlation. So 2 plus 2, there are 4 correlation, 4 velocity fields, and when they combine them, I get 2 velocity fields here. These are the 2 velocity fields. So this is the diagram. So when I expand U1P, I'll get another diagram. Expand U1Q, I get another diagram. So this is, if I compute contribution from these diagrams, I can get the flux. And this for U1 channel, and you also have for U2 channel. Okay, this is U2 channel. So I need to compute these guys. Okay. Now, assuming Kolmogorov and assuming form of this viscosity, I can compute these guys. It turns out these integrals are finite. They do not suffer from ultraviolet divergence. Of course, I'm going to put Kolmogorov stuff. It converges. Also, I want to remark that there is no infrared divergence problem. In RG, it is fixed. RG is in fact devised to fix the infrared divergence. There is no divergence at low wave numbers. So divergence are gotten rid of in this case. So when I integrate them, I get the flux. I will not discuss this part. These are also very interesting insights. It also talks about local energy transfers, but I will skip this part. So given SS, I can compute the flux, which is integral of S. So once I know how the energy goes from a wave number to another wave number, energy flux is energy going from all the modes within the sphere to modes outside the sphere. So it's an integral, and that's the integral. Okay, and this integral gives me some stuff. So the final equation is, so I think is here. This is what I want to write. So this is my flux, which is integral of this S. Now, when I do some bit of juggling around with variables, I get this equation, which is pi flux at a radius r. So r is the radius of the sphere. Okay, so radius sphere divided by epsilon u, which is dissipation rate, which is right hand side is the integral. And I said this integral is finite. I get a number, and this is proportional to a constant a, which is proportional to k to the 3/2. This Kolmogorov constant, non-dimensional constant to the 3/2. So what about this number? In the inertial range, flux equal to dissipation rate, right? And of course, I'm assuming that my inertial range is infinite from both sides, small and large. So this number is 1. This number is, well, I'm doing it for various components, but I have sum over all the components, I will get 1. So by left hand side becomes 1 if I sum over all components. So then I can get value of A, and from that I can get value of constant, Kolmogorov constant. So Kolmogorov constant is here. Okay. So the 2 ways to compute Kolmogorov constant, I cannot discuss the subtle difference, but this constant for 3D is around 1.67. It turns out for me, for all dimensions greater than 3, they are roughly equal. For d equal to 2, I get around 4.6. The numerical solution is something like 6 point something, okay? Depends on who's giving you the number, but 2D is 4.6. I also get for 2D, I get this number to be negative. That means it's inverse cascade for 2D. We get this from this calculation. The redenominator viscosity is positive, but flux is negative. Okay, so I think I'll skip this part. So flux is negative here for 2D. There's a crossover at around 2.15. Okay, so sign of this flux changes from negative to positive at dimension 2.15. Okay, so I think I'll skip this past work. So this is a nice paper which was told by York. I looked at it, and the Kolmogorov constant is roughly equal, but they go up to 200, which I believe is not correct because the viscosity was not calculated by them, Goto's group. So viscosity is not here. They model it by eddy viscosity, but this seems to be reasonable from what I presented. So conclusion. So d-dimension turbulence, K minus 5/3 is a solution for d less than equal to 6, less than 6. And so at 2.15, which I didn't show very clearly, at 2.15, there's a change of energy cascade direction. From negative, it becomes positive. It may be interesting to, simulation wise, I don't know how complicated that is. It's probably not so easy to compute. So field theory does provide valuable information. I also make a remark that I have nothing on intermittency. So this is only energy flux and redenominator viscosity. Okay, so I'll end with this slide and thank you.
Yeah, thank you very much. Questions?
Earlier, when I said we don't know how to calculate the Kolmogorov constant, of course, I was aware of these calculations,
okay,
but I don't know how much of it is put in by hand and how much of it really is calculated a priori. I mean, somehow you should maybe reassure me that not a lot is put in by hand.
Okay, so Kolmogorov formula is put in hand, and the constant 5/3 spectrum is put in by hand, and K naught comes out of it. In this scheme, in Yoko-Dodson scheme, the forcing spectrum is put in there, and then you have to choose d equal to 4, right? So that's the input there. So every scheme has this subtle assumption. Yes, so that with that caveat, I agree, but it comes out of with that. And also it's first order, we are not doing more diagrams. So.
Okay, are there further questions? Luca.
Thank you, Mahendra. In the case where you don't have transfer pi equal to 0, this is d equal to 2.15, right?
Yes.
Yeah. I mean, I wonder if you could have some kind of thermal equilibrium in this situation.
No. So it's a very nice question. Let me take this, for me going back all the way. So it turns out if you look at the velocity field, let me just write it here. The S part, KPQ, is 3 U's, right? U. So for the equilibrium solution, this is 0 all right away. And you don't need to go to higher order because it's exactly 0. So stop there. But d equal to that, what, 2.15 is when you have 5/3 put in as a solution. So inverse cascade of 2D, or well, I'm putting Kolmogorov spectrum and I'm seeing 0 flux at d equal to 2.15. That is with Kolmogorov spectrum, but this is Euler solution has 0 flux. So that straight away follows. We don't need to do any field theory for Euler or perturbation.
Okay, yeah, one more question.
So when you have 6 dimensions, you're assuming you have boundary conditions in Fourier space, right? You're injecting energy at small wave numbers, and you assume you have a sink at very large wave numbers.
Yes.
So I don't understand how you can get equilibrium, so zero flux solutions with those conditions, right? Because energy, I would expect it has to be transferred to your sink.
So it's possibly, well, it's a good point. So possibly it equally distributes. So K phi theta is unequal distribution, but it's possible that it will equally distribute among all the modes and reaches that steady state. So you have to cascade, but here it maintains that cascade. It's possible that boom, it equally distribute, but at the end possibly something happens. So yeah, that's a conjecture, but I don't know. We need to see how you distribute wealth is communist system or capitalist system. That's
Okay, thank you very much,
Thank you.
Mahendra. And I think we have to move on.